So we're asked to find something about the derivative of the inverse of a. So in a different video we derived this little nifty formula. It was obviously written by a 4-year-old with a crayon. I'm sorry. I've been getting worse, not better, with drawing with a mouse. But basically what it says is that if you need to know something about the derivative of the inverse, then from the chain rule we can find something to represent the derivative by plugging in information over here on the right. It's the derivative of the original f of x as a composite with f of x inverse. So it basically means you plug the inverse into the derivative of f of x. So the derivative of f of x is easy for this one. The 1 comes down, gets reduced by 1, it's just -5. So there's actually nowhere to plug in the inverse into the derivative of the original function. Can't plug this in because there's no x. So it's just 1 over -5. So it doesn't matter what a is. The derivative of the inverse for this particular function is always -1 over 5. So if you need to say something about the derivative of the inverse, we need to say, here's the inverse, and we want it at a equals 2, so that means we're plugging in 2 into the inverse function. Then we can use that notation that we saw, it's in the textbook. The textbook gives you the formula for the derivative of an inverse function. We derived it in one of the other videos here this week. It's f prime of the inverse at 2. So it'd be nice if we knew what this was, okay? We don't, though, because we know, unlike the other questions where we've done these derivatives of inverse problems, we usually have an x and a y pair for the inverse. So we don't know what the y value is when x equals 2 in the inverse function. But what we can do is we can use what we know about inverses. The x in an original function is the y in an inverse function. So the x in the inverse function is the y in the original function. So this is a y value in the original function. So if you solve that equation for x, raise both sides to the 4th power, subtract both sides by 4, divide both sides by 3, then x is going to be 4. So this is going to be 4 because the corresponding output, when you input 2 into the inverse, is 4. So this is f prime of 4. Okay, so we just need to know what f prime is. So we need to take a derivative of the original function. So that 4 up there means it's a 4th root. This whole thing is being raised to the 1/4 power. So 1/4 comes down, and then it gets reduced by 1. So 1/4 subtracted by 1 is going to make -3/4. But that's a derivative of the 4th root, the outermost function. Ignore the 4th root now and look inside. There's a function inside of it, so we need the chain rule. Got to multiply this by 3. So that's the derivative of the original function. So we're just supposed to plug in 4 into this. Let's see. So if we do that, inside the parentheses, 4 times 3 plus 4, raise that to the -0.75 power, that's -3/4, times that by 1/4, and then times 3. So we get this in the denominator. Probably could have just kept it as some nice looking fractions, but I don't have the handwriting capacity for that right now with this mouse. So 1 divided by the decimal, 10.6 repeating, so 10 2/3, which is 32 over 3. So one last one. So the inverse at 1/4, and we want the derivative. That is 1 over the derivative of the original f of x with the inverse as inverse plugged into the derivative. Oh boy, what should we do first? I mean, let's do what we did in the last video. Let's find out in the inverse function, if you have 1/4 for x, you need to find the corresponding y in the inverse function. But if 1/4 is x in the inverse function, then its corresponding value in the original function would be a y value. So we need to plug in 1/4 in where the response variable would go. Oh boy, some algebra here. To get x by itself, I'm going to multiply both sides by 3x plus 2. Distribute that fourth, and I'm going to use decimals. I don't know why. And then I'm trying to get x by itself, so I'm going to add 1x to both sides. So it makes 1.75x plus 0.5 equals -3. So subtract that, 0.5 from both sides, and then divide 1.75 from both sides. So 3.5 divided by 1.75, that makes -2. Okay, so -2 in the original function for x gives us 1/4 for y. That means -2 is the response variable here. So this is -2. Now we just need to know what the derivative of f is. And looks like quotient rule might be best there. The derivative of the original function, this is like the numerator and this is the denominator. So the quotient rule says it's the derivative of the denominator times the numerator kept the same, subtracted by the original numerator times the denominator, divide by the denominator squared. So we want to know here the inverse of f at 1/4 was -2. So this is what we really want to know. We want to know what the value is of the derivative when you plug in -2 in for x. Right? Here, I'll write out that notation. We just found out what this is by plugging in some numbers. We found out that 1/4 corresponds with -2. So this is what we're trying to evaluate off to the side. Once we have that, we can finish out the problem. So if we plug -2 in there, -2, I'm just putting +2. Three times -2 makes -6. -6 plus 2 makes -4. -4 times 4 gives us 4. Okay, let's write that down before I forget it. And then over here, 2 minus 3 makes -1. -1 times 3 makes -3. Minus a -3 means +3. And then here, 3 times -2 makes -6. -6 plus 2 makes -4. -4 squared is something. 16, right? So 4 plus 3 makes 7. So 7/16 is what needs to get plugged in here. So it's just the reciprocal, right? 1/7/16. That's the same thing as 16/7.